All right, everyone. Welcome back to a new unit, application of Newton's laws. Hopefully, you guys all did the chapter on Newton's laws already. Today, we're going to be discussing primarily about video problems, but just a quick recap about Newton's laws. I'm not going to go too much into it because this should be about elevators laws, but if you want to kind of pause the video and just take notes, please do that. 3 by diagrams. Okay, elevator problems. Scenarios such as elevators where the platform can accelerate either up or down will change the amount of contact between contact objects have with the floor, changing the normal force experience. So you guys should have probably experienced this whenever you've been inside of an elevator. When you either start going up or start going down, your body should feel a little bit different. And it's going to feel a little bit different where it's going to be slightly heavier or slightly lighter. And I know when I was a kid, I used to jump in the elevator because I was like, this is an interesting phenomenon. I wonder if I could jump higher or things like that. So I would try that. Maybe not recommend it. It might break the elevator, but we're going to talk a little bit about this phenomenon. Okay, so let's do this. A person is messing around in the elevator and brings a scale to stand on as the elevator goes up and down. At what point will the scale read the highest amount of weight? A, when the person is accelerating up. B, when the person is accelerating down. C, when the person is going up with constant velocity. D, when the person is going down with constant velocity. E, scale will read the same no matter what. One thing I guess I want to say right from the beginning is when it's going with constant velocity, that means that acceleration is equal to 0. And when acceleration is equal to 0, that means there's going to be no effect on, I guess, what the scale will read in this situation, or how your weight will feel like it's different. But let's talk a little bit more about this. So the answer here is when you're accelerating up. And the reason should be kind of intuitive. So when you're accelerating up like this, what's happening is your body here, right? It wants to stay in the same position, but the platform is raising up fast. And what's happening is that means that since your body kind of wants to stay here, it's kind of getting squeezed down. So there's kind of like this extra pressure down, and that extra pressure is making you feel heavier, pushing more force onto the scale and making it read more. Okay. It's kind of like the opposite when it's going down. When it's accelerating down, it's almost as if you're getting lifted off of this. So you're pushing down because gravity is pulling you down. But when it starts to accelerate down, now there's not as much pressure down here because it's almost like the platform is going from under you, like trying to get away from you. Okay, so there's not as much pressure with you, contact with you. Okay, and this contact that we talk about, actually, it's not talking about contact, so we'll talk about that a little later. Okay, a person that has a weight of 800 Newton goes into an elevator with the scale from the ground. The elevator initially starts to accelerate upward, then goes up with a constant velocity. How does this motion affect the scale's reading? The scale will read 800 newtons the whole time. The scale will read greater than 800 newtons the whole time. C, the scale will read less than 800 newtons the whole time. D, the scale will first read greater than 800 newtons, then it will read 800 newtons. E, the scale will first read less than 800 newtons, and it will read 800 newtons. So just letting you know, this was something that is actually going to happen if you want to bring a scale to an elevator. Yes, I have actually done this, but it's pretty cool. Okay, so that being said, what's going to happen is at first it's going to accelerate, right? While it's accelerating up, remember we're going to have more contact with the ground because it's as if the platform is pushing up against you more. So since there's more contact, what that's going to be is the normal force is going to increase. And since the normal force increases here, the scale is going to read greater. So it will read greater, but when it starts to travel with a constant velocity after it's done accelerating, there's no longer any more acceleration, and that means it will read 800 newtons after. So it won't be the whole time. Okay, so while it's accelerating, it will be more than 800. Then it will go back to 800 because it's no longer accelerating. Okay. All right, moving on. person that has a weight of 800 newtons goes into an elevator with the scale from the top. The elevator initially starts to accelerate downward, then starts to go down with a constant velocity. How does how does this motion affect the scale's reading? So pretty similar to what I said in the last slide. So you could kind of look at that. But the scale will first read less than 800 newtons, and then it will read 800 newtons. Again, the reason for that is while it's accelerating downward, there's not going to be as much contact with the ground because the platform is kind of like moving away from it, so you won't have as much contact or as much normal force. So it'll read less than 800 newtons at the beginning. But once it starts traveling with a constant velocity, that means acceleration is zero, and it will read 800 newtons. Okay, moving on. Conceptual example number 4. For each of the stages, will the scale read greater, less, or equal to the person's weight? Okay, so let's look at this. The first stage over here, the constant speed, it's going up or down with constant speed. I guess it doesn't say, but that we can see that the acceleration is equal to 0 meters per second squared. So in this situation, what do you think it'll be? Will the scale read more, less, or equal to the person's weight? It's going to equal, and the key thing here is constant speed, and we should know that the acceleration is 0. So when the acceleration is the same, that means that the force of gravity and the force normal are going to be equal to each other, and the scale reads what the normal force is. So the scale reads how much pressure, how much contact there is with the ground. So if it's going to be the same, then it's going to be equal. Okay, upward acceleration. When it's accelerating upward, we've done enough problems like this, so you should know, but it is going to be greater. And because it's accelerating downward, that means there's going to be a lot more pressure going down. It's almost like the person's being squeezed. And when that's the case, that means the normal force is going to be a lot more because there's a lot more pressure that's having in contact with the ground right here. Downward acceleration 5 meters per second squared is going to be less. And again, it's as if like the platform is like trying to run away from the person. So what's happening is there's not going to be as much contact, which also means normal force will be less. And downward acceleration of 9.8 meters per second squared. This is like gravity. I know we've been using 10, but if it's going the same as gravity, it's almost as if you're just going to be kind of like floating in there, which is a little bit weird to think about, but it's going to be 0 because you're both kind of falling at the same rate, so you don't have any contact with the ground. Okay, there's essentially no contact with the ground. So that would happen if the elevator ever just snaps. So you'll be just falling, you'll be floating in there until you fall to your doom. Okay, real life example. There are airplanes that use this concept of acceleration to imagine what it would be to be on Mars, the moon, or space. These planes accelerate up and down at different rates to change your weight throughout its motion. The plane's something like this. Okay. So there's a video of it, but it's pretty cool. Like it goes up and down like this, and how it goes up and down, it can change how you feel. So if it's accelerating up really high, you're gonna feel extremely heavy. And if it's accelerating down really fast, depending on how fast, it could feel like you're on the moon, it could feel like you're on Mars, or it could feel like there's no gravity at all, like space. And you should watch the video. I can't show it here because of copyright things, but you should watch the video. Okay. Next example here. First math example. Charlie owns a shady donut business in the elevator. Charlie sells donuts by the Newton. Each donut has a mass of 0.8 kilograms, and Charlie uses a scale to weigh the donut. When should you weigh the donuts to get the best deal? Okay, so if this donut shop is in the elevator, we should know that these donuts are going to weigh the least when it's accelerating downwards. Okay, if it's accelerating up, it's going to weigh more. If it's going with constant speed, or if it's not moving, it's going to be the same amount. But you get the best deal when it's accelerating downwards. Okay, what is the weight of one of the donuts when the elevator starts to go down with an acceleration of 2 meters per second squared? Okay, so let's look at this. And what we're going to do is we're just going to draw a free body diagram. Okay, so this is a donut. So we know that the donut is going to have a force of gravity, which is the mass of one donut is 0.8. So this is going to be 8 newtons. It's a huge donut. And then there's going to be a normal force. Okay. That's what the scale is going to read. We don't know what this is. Okay. But we do know that it is accelerating downwards at 2 meters per second squared. Okay, so let's do this. Sum of all forces in the y equals mass times acceleration in the y. There's two forces in the y. Force normal going up, force of gravity going down, mass of the donut times acceleration of the donut. We don't know the normal force, but we do know force of gravity is 8, and we do know mass is 0.8, and we do know it's accelerating down 2 meters per second squared. Okay, if we do that, now we can use a calculator. Um, and do 0.8 times -2. So maybe I'll write this out a little bit more. Force normal minus 8 is equal to negative 1.6. And then I'm going to try to isolate this force normal. So I'm going to add plus 8 to both sides. And then I should know force normal is going to equal to 6.4 newtons. Okay. Okay, so part C here is, so it's going to weigh less, kind of like how we confirmed with part A. Part C here says, what is the weight of one donut as the elevator travels down with a constant speed of 5 meters per second? Okay, so constant speed here is telling us that the acceleration is equal to 0. Okay, so if we know that, maybe I'll just show this because this is the first time we're doing a problem like this, but in the future I probably won't. So we know force of gravity is equal to 8 newtons. Don't know what the normal force is, but we do know that the acceleration is equal to 0. Okay, so if we write this all out, sum of all force in the y equals mass times acceleration in the y. We don't know normal force. We know force of gravity is 8. We know the mass is 0.8, and we know the acceleration is 0. So this now shows force normal minus 8 equals 0. We can bring 8 to the other side, and we can just say force normal is equal to 8 newtons. So the weight of one donut is going to be 8 newtons. Okay. So anyway, that just shows when it's constant speed, the force of gravity and then force normal is going to be the same. So the scale will read the same thing. Okay. Part D is, what is the weight of one donut when the elevator starts to go up with an acceleration of 2 meters per second squared? Okay, so let me just kind of erase all this. Very similar to part B, but instead of accelerating down this time, we're going to be accelerating up. So you should be able to do this on your own, and I suggest doing that. If I suggest always trying to do things on your own. So, but anyway, here I go. If you don't want to do that. Okay, part D. And maybe I'll do a little faster this time. Donut, force of gravity, 8 newtons, accelerates up 2 meters per second squared. What is the scale going to read, which is the same as what is the normal force? Sum of all force in the y equals mass times acceleration in the y. We have force normal going up, force of gravity going down, the donut 0.8, which is accelerating up 2. So force normal minus 8 to 1.6, add 8 to both sides. Force normal is going to equal 9.6 newtons. Okay, I hope that helps. I hope that makes sense. That was our first mathematical problem, so hopefully it wasn't too bad. Okay, similar kind of problem, so hopefully you can do it on your own. A rocket ship will accelerate into space at a rate of 15 meters per second squared. If one of the astronauts has a mass of 75 kilograms, what would the normal force she would be experiencing during takeoff? What would be the normal force she would be experiencing at takeoff? Okay, so let's just draw this astronaut as a box. This box here, or this astronaut, has a force of gravity of 750 newtons. And then we don't know what the normal force is going to be. This is how heavy she's going to feel. But we do know accelerating at 15 meters per second squared. It's a lot. Okay, so let's plug this all in. Especially if you're able to do the last one or understand the last one, this should be fine. But we have force normal going up, force of gravity going down, mass of the astronaut, and the acceleration of the astronaut. Don't know the normal force. We do know force of gravity is 750. We do know the astronaut is 75 kilograms, and we do know he's accelerating up 15 meters per second squared. I'm going to put this into my calculator. 75 times 15. And then I'm going to put 750 to the other side, so plus 750. And it's going to be 1875 newtons. Okay, hope that makes sense. All right, so a little bit of a refresher here. Pause the video, but this is from kinematics, and it just shows, the formula for acceleration. So if you need this, just pause it and look at it. And we're going to use this for the next example. Okay, a red penguin has a mass of 2.2 kilograms in an elevator that is about to go up. The elevator starts from rest and reaches a speed of 4 meters per second in 2 seconds. After 2 seconds, it coasts up with a constant speed of 4 meters per second. During the first 2 seconds of the elevator ride, what normal force did the penguin experience? Okay, so this is kind of like a few step problem here. First, what we need to figure out is, what is the acceleration? We know it starts with the initial velocity of 0 because it says the elevator starts from rest. Oops, yeah, let me do 0 here. Okay, that's not a great 0. Do 0 again. And then we also know it's going to take a time of 2 seconds to reach a speed of 4 meters per second. So we're going to kind of go back to that formula here, and we're going to figure out what acceleration is. Oops, sorry. I don't know what I just did. Okay, so acceleration is equal to v final minus v initial divided by time. So this means 4 minus 0 divided by 2, which is going to be 2 meters per second squared. Great. Now we know what the acceleration is. We can use that to help us find the normal force. So first of all, let's draw out this penguin as a box. The force of gravity of this penguin is going to be 2.2 times 10, which is 22 newtons. We don't know the normal force. We don't know how much he's going to be squeezed in that elevator. But we do know that this penguin is going to be accelerating up 2 meters per second squared. Okay, so let's write this all out. Sum of all forces in the y is equal to mass times acceleration y. So we have normal force going up, force of gravity going down, mass of the penguin, acceleration of the penguin. Okay, force normal we don't know, force of gravity of the penguin 22, mass of the penguin 2.2, and it's accelerating up 2 meters per second squared. Okay, let's do the math. 2.2 times 2. And then let's put the 22 on the other side, so plus 22. And we can see that the penguin is going to be 26.4 newtons. Okay, great. Now let's look at part B. And I'm not going to explain too much of this because I did in previous problems. But after the first 2 seconds of the elevator ride, what normal force did the penguin experience? So we should know after the first 2 seconds, let me see that. After the first 2 seconds, it coasts up with a constant speed of 4 meters per second. So this constant speed is telling me that the acceleration is equal to 0. And if the acceleration is equal to 0, what I should know about that is the force of gravity, which is equal to 22 newtons, is going to be equal to the normal force. These two are going to cancel out with each other because the acceleration is equal to 0. Okay? So after what is the normal force, it's just going to be 22 newtons because there's no acceleration. Okay, let's look at this example. A zebra of a mass 92 kilograms is in an elevator that is about to go up. The elevator is moving toward the top floor at a speed of 5 meters per second. The elevator suddenly slows to a stop in 2 seconds. During these 2 seconds of the elevator ride, what normal force did the zebra experience? Okay, so a few things going on here, kind of similar to last problem. We got to figure out a few things. First, the elevator is going at a speed of 5 meters per second. Okay, that's how it's going initially. And then it's slowing to a stop in 2 seconds. So after 2 seconds, it slows to a stop, meaning the final velocity is 0. And we need to use this information to find out what is the acceleration going to be. And like last time, we're going to be using the acceleration formula to figure that out. So we have 0 minus 5 divided by t, which is 2. So this is going to be equal to negative 2.5 meters per second squared. So one big thing that we should be able to see from this is the acceleration is actually pointed downwards. And that might seem a little bit strange because the elevator itself is moving upwards. However, it's moving upwards, but it's slowing down. So if you remember that, whenever something is slowing down, the acceleration is going to be in the opposite direction. But anyway, the math also tells us what direction it is. So if you're confident in your math, you should be good. Okay, now that we know the acceleration, let's draw this zebra as a box. And then what we know that the force of gravity of the zebra is 92 times 10, which is 920 newtons. We don't know the normal force, but we do know it is accelerating down during that time, 2.5 meters per second squared. Okay, sum of all force in the y is equal to mass times acceleration in the y. The normal force minus gravity, mass of the zebra, acceleration of the zebra. Don't know the normal force. Force of gravity is 920. Mass is 92. And acceleration is negative 2.5. Okay, let's do some math. 92 times negative 2.5. And then I'm going to add the 920 to the other side. Plus 920. And we get 690 newtons. Okay, hope that makes sense. All right, let's look at this. Which of the following situation or situations is the elevator accelerating in the upward direction? When the elevator starts to speed up in the upward direction, when the elevator starts to speed up in the downward direction, when the elevator starts to slow down in the upward direction, when the elevator starts to slow down in the downward direction, when the elevator is moving up with constant velocity in the upward direction. So we need to kind of look at everything because there could be multiple situations. So first one, when the elevator starts to speed up in the upward direction. So that, like for example, when it starts from rest and starts to go up fast, that is going to be accelerating upwards. Whoops, sorry, giving the answer away. So it should be A here. And most of you probably got that. B, when the elevator starts to speed up downward direction. No, when it starts to go downward, we should know it's going to be accelerating down. So it shouldn't be B. C, when the elevator starts to slow down in the upward direction. Okay, so when it's going up, so it's moving up in this situation, but it's slowing down. So if it's slowing down, that means acceleration is going to be in the opposite direction of the velocity. So that means it's going down. So it won't be C. When the elevator starts to slow down in the downward direction. Okay, so that one is kind of the opposite of what we just did. So it's going down, but it's slowing down. That means acceleration is going to be the opposite direction, going up. So it should be D. When the elevator is moving with a constant velocity in the upward direction. No, acceleration is 0 during that time, so this is just going to be like that. So these are the answers. Hope that makes sense. We're going to do a similar one right here, so hopefully you guys can figure that out. Which of the following situations the elevator accelerates in the downward direction? Okay, when the elevator starts to speed up in the upward direction. We just kind of talked about that, but no, when speeding up in the upward direction, that means accelerating up. When the elevator starts to speed up in the downward direction. Yep, most of you guys probably got that. When the elevator starts to slow down in the upward direction. Okay, so it's going up, but then it starts to slow down, meaning the acceleration, whenever it slows down, the acceleration is in the opposite direction of velocity. So that's down. So yes. When the elevator starts to slow down in the upward direction, nope, that's going up. Moving constant velocity, nope, that means acceleration is 0. Okay. All right, guys, that was kind of a lot. I hope that all made sense. Next time we're going to be talking about tension, so I hope to see you with that. Thanks for watching, everyone. Bye.